A good way to start a problem like this is to inspect the circuit visually to see what sorts of constraints and relationships you can extract from it. Let's look at this voltage source V3. It's going to tell us that V1 is equal to V2 plus 1. Now, although we don't have exact values for V1 and V2, we at least know that V1 should be equal to V2 plus 1. This is going to be a relationship that we save for later. If we look again at this voltage source, we see that V1 and V2 are two non-reference nodes that share V3 between each other. So what this means is that instead of writing two individual KCL equations, we can write one KCL equation for what is called a supernode. Now, a supernode sounds more complex, but it saves us because what the supernode equation agrees to do is take all four currents in these branches and balance them out in one formula. I want to show you what that looks like for each of these terms. Now, for KCL, I'm going to use this convention above. It states that the sum of the currents entering the node is equal to the sum of the currents leaving the node. This can also be written as the sum of the currents leaving the node is equal to the sum of the currents entering the node, or that the sum of all the currents entering and leaving is set equal to 0. These are all saying the same thing. It's down to personal preference. Let's take R1, our first resistor. What we're going to have is V1 minus 0 over 1 ohm. We get this because the positive lead is at V1 and the negative lead is at ground. And remember, a voltage reading or a voltage calculation is a difference between 2 points. So make sure whichever node is at your positive lead is listed first. The next term is going to be the current source, 2 amps. We can simply write 2A. Let's set that equal to the other half of our KCL formula. We're going to start with this other current source, 1A. Let's add that to R2, the last resistor. Now, pay attention to my leads. It's going to require me to write it as 0 minus V2 over 1 ohm. The next step is going to be algebraic simplification. We're going to take this first fraction and simplify it just to V1. We're going to take 2 amps. We're just going to write 2. Same thing for 1 amp. We're going to subtract a V2 as we can simplify this fraction to negative V2. Now, what I want to do is I want the V1 and V2 on one side, and I want the constants on the other side. So I'm going to subtract 2, and I'm going to add V2. And that's going to give me V1 plus V2 is equal to negative 1. This is going to be an equation we save. Now, if we go back to our voltage source constraint, we have a relationship that we can substitute in for V1. So when we do this, we have V2 plus 1 plus V2 as we've substituted in for this V1 term over here. We set that equal to negative 1. If we simplify this, we combine the two V2 terms and get 2V2, and we send this one to the other side of the equal sign, and we get negative 2. We're going to divide both sides by 2 to get the V2 alone. That's going to give us V2 is equal to negative 1. Now that we have a value for V2, our next step is going to be substituting that in for our equation up here. V1 minus 1 is equal to negative 1, which is going to give us that V1 should be equal to 0.